Imagine building a railway across the highest plateau on Earth, where the air contains nearly 40% less oxygen. The ground melts beneath your feet, and winter temperatures fall below -40 degrees. Most engineers called it impossible. China called it a construction project. Railways have always followed one simple rule: avoid mountains whenever possible. Find the easiest route. Reduce steep gradients. Minimize tunnels. Control construction costs. The Qinghai, Tibet Railway ignored every one of those rules, stretching across some of the most extreme terrain on Earth. It climbs higher than any railway ever built, crossing frozen ground, active seismic zones, violent snowstorms, and vast stretches of uninhabited plateau where construction crews worked at altitudes high enough to affect both the human body and heavy machinery. For decades, many engineers believed a railway across Tibet simply couldn't be built with existing technology. Not because laying tracks was impossible, but because keeping those tracks stable year after year seemed almost unattainable. Yet today, passenger and freight trains travel this route every day, quietly crossing one of the harshest environments on the planet. Behind that achievement lies one of the most ambitious engineering projects of the modern era. On most railway projects, engineers worry about gradients, bridges, or tunnels. On the Tibetan Plateau, they had to worry about the ground itself. The Qinghai, Tibet Railway crosses one of the highest and most hostile landscapes on Earth, with long sections built at elevations exceeding 4,000 meters above sea level. At these heights, oxygen levels are dramatically lower than at sea level, reducing worker productivity, affecting construction equipment, and creating serious health risks for crews operating in remote locations. But thin air wasn't the greatest challenge. The real enemy was hidden beneath the surface: permafrost. At first glance, permafrost appears solid and stable. It looks like ordinary ground, but it behaves very differently. Permafrost is soil that remains frozen for years, sometimes thousands of years. When it stays frozen, it can support enormous loads. But once it begins to thaw, its strength rapidly decreases. Ice trapped inside the soil melts into water, causing the ground to soften, settle, and deform. For a railway, even small movements can become dangerous. A few centimeters of uneven settlement may change track alignment. Over time, that can increase vibration, accelerate wear, and compromise operational safety. Traditional railway foundations couldn't solve this problem. Concrete foundations often trap heat. Passing trains generate additional thermal energy. Even sunlight absorbed by embankments can slowly warm the frozen ground below. Ironically, building a stronger foundation could actually make the railway less stable. Chinese engineers quickly realized they weren't simply constructing a railway. They were building on ground that could literally disappear beneath the tracks if its temperature changed too much. So before laying even a single rail, they first had to answer an extraordinary engineering question. How do you keep the Earth itself frozen while running trains across it? Keeping frozen ground cold may sound easy. After all, the Tibetan Plateau is one of the coldest places on Earth. But for engineers, cold wasn't the problem. Heat was. Every passing train transfers heat into the rails. Steel absorbs solar radiation throughout the day. Concrete embankments store thermal energy. Even the natural summer season slowly warms the surface. Over time, that heat travels downward. If it reaches the permafrost, the frozen soil begins to thaw, and once thawing starts, the ground loses its strength. Instead of fighting this process with refrigeration systems, Chinese engineers designed something far more elegant. They allowed nature to do the cooling. Thousands of specially designed thermosiphons were installed beneath critical sections of the railway. At first glance, they look like ordinary metal pipes, but inside each sealed tube is a working fluid engineered to move heat without using electricity or mechanical pumps. During winter, the frozen air above the ground becomes much colder than the soil below. The liquid inside the thermosiphon absorbs heat from the permafrost and evaporates. The vapor naturally rises toward the colder upper section of the pipe. There, it cools, condenses back into liquid, and flows downward again under gravity. The cycle repeats continuously. No motors, no external power, no moving parts, just physics. These passive cooling systems continuously remove heat from the ground, helping maintain frozen soil beneath the railway year after year. But cooling pipes alone couldn't solve every problem. Some sections of the plateau were simply too unstable. Engineers needed an entirely different way to support the railway. Most railway bridges cross rivers or valleys. The Qinghai, Tibet Railway broke that rule. Across large sections of the plateau, engineers built long, elevated bridges over perfectly flat land. At first, that makes very little sense. Why build an expensive bridge where there's nothing underneath? The answer, again, was permafrost. A traditional railway embankment places enormous weight directly onto the frozen ground. That weight compresses the soil. At the same time, the embankment traps heat, preventing cold air from naturally reaching the surface below. Over several years, the frozen ground begins warming. Settlement follows. Track alignment changes. Maintenance costs increase dramatically. Elevated bridges solved both problems. Instead of spreading thousands of tons of load across the surface, engineers transferred the weight into carefully designed deep foundations located in more stable ground. Even more importantly, cold air could continue circulating freely beneath the bridge deck. The wind naturally removed heat from the surface, slowing the thawing process below. In other words, the bridge wasn't built to cross water. It was built to protect the ground. This strategy significantly reduced long-term deformation while improving track stability across some of the railway's most vulnerable sections. It was a remarkable example of engineers redesigning the landscape, not to support the railway, but to preserve the environment supporting the railway. Yet despite solving the ground problem, engineers still faced another enemy, one that couldn't be frozen or bridged: the air itself. Constructing a railway at sea level is already a massive undertaking. Building one above 4,000 meters changes everything. At these elevations, the atmosphere contains significantly less oxygen than at sea level. For construction workers, simple physical tasks become exhausting. Fatigue appears more quickly. Reaction times slow. The risk of altitude sickness increases dramatically. Even experienced crews require time to acclimatize before working safely. Heavy machinery also suffers. Diesel engines rely on oxygen for combustion. With thinner air, engine performance decreases. Fuel efficiency changes. Cooling systems become less effective. Equipment that performs normally elsewhere may struggle on the Tibetan Plateau. Chinese engineers adapted both people and machines to these extreme conditions. Construction camps were equipped with oxygen supplies and medical facilities. Workers followed carefully planned shift rotations to reduce prolonged exposure to high altitude. Special maintenance schedules kept heavy equipment operating efficiently despite the reduced air density. Every construction activity, from pouring concrete to transporting steel, had to account for conditions rarely encountered on conventional railway projects. Because on the Tibetan Plateau, the engineering challenge wasn't simply building a railway. It was building one in an environment where both humans and machines operate below their normal limits. And once construction was finally complete, the next challenge began. How do you safely operate passenger trains at the highest altitude on Earth? Building the railway was only the first challenge. Operating it safely presented an entirely different engineering problem. The Qinghai, Tibet Railway climbs to an altitude of more than 5,000 meters above sea level. At that elevation, atmospheric pressure drops dramatically. The air contains far less oxygen than most people are accustomed to breathing. For healthy passengers, this can lead to headaches, fatigue, dizziness, or even altitude sickness during long journeys. Simply running an ordinary passenger train wasn't an option, so engineers redesigned the train itself. Every passenger coach is built with a sealed, pressurized cabin, similar in principle to the cabin of a commercial aircraft. Instead of allowing outside air to enter directly, the train maintains a carefully controlled internal environment. Additional oxygen is continuously supplied through an onboard distribution system. Passengers can breathe enriched cabin air throughout the journey. Individual oxygen outlets are also installed beside every seat and sleeping berth. If someone begins experiencing symptoms of altitude sickness, supplemental oxygen can be used immediately. Even the ventilation system had to be specially engineered. Fresh air enters through advanced filtration equipment before oxygen concentration is adjusted and distributed evenly throughout each carriage. The goal isn't to recreate sea-level conditions. That's impossible. Instead, engineers create an environment where most passengers can comfortably complete one of the world's highest railway journeys. But keeping people alive was only half the challenge. Keeping the railway itself alive would require constant monitoring long after construction ended. Most railway lines are inspected on a regular schedule. The Qinghai, Tibet Railway couldn't rely on routine inspections alone, because the greatest threat wasn't visible. It was happening beneath the tracks. Permafrost is constantly changing. Ground temperatures rise and fall with the seasons. Small variations can slowly alter soil strength over time. A track that appears perfectly stable today could begin settling months later. To detect these changes before they become dangerous, engineers transformed the railway into a continuously monitored infrastructure system. Temperature sensors are embedded beneath critical sections of track. Ground movement is measured using high-precision surveying equipment. Weather stations record wind, snowfall, solar radiation, and air temperature throughout the year. Inspection trains equipped with advanced laser measurement systems regularly scan the rails. Even tiny changes in alignment can be detected long before they affect passenger safety. If a section begins showing unusual settlement, maintenance teams investigate immediately. Sometimes the solution is adjusting the ballast. Other times, engineers reinforce foundations or improve drainage around vulnerable areas. The objective is predictive maintenance. Don't wait for a problem to appear. Identify it while it's still almost invisible. This engineering philosophy has dramatically improved long-term reliability across one of the world's harshest railway environments. Yet despite constant monitoring, another challenge remained, one that had nothing to do with trains or frozen ground: the Tibetan Plateau itself. The Tibetan Plateau is more than an engineering challenge. It's one of the world's most fragile ecosystems. It supports unique wildlife found almost nowhere else on Earth. Building hundreds of kilometers of railway across this environment carried significant environmental risks. A continuous embankment could divide animal migration routes. Heavy construction might disturb wetlands. Changing natural drainage patterns could permanently affect frozen landscapes. Engineers therefore designed many sections of the railway to minimize environmental impact. Long elevated bridges allow animals to pass beneath the tracks without crossing active rail lines. Special wildlife corridors were incorporated into the route to reduce habitat fragmentation. Drainage systems were carefully planned, so seasonal meltwater could continue flowing naturally instead of becoming trapped behind railway embankments. Construction teams also adopted strict environmental management practices in sensitive areas, reducing unnecessary disturbance and carefully controlling waste generated during the project. The objective wasn't simply to build the railway. It was to ensure the plateau could continue functioning as a natural ecosystem long after construction had ended. Balancing infrastructure with environmental protection remains one of the defining engineering challenges of the 21st century. And perhaps nowhere is that balance tested more dramatically than here. But after overcoming frozen ground, extreme altitude, complex logistics, and environmental constraints, one final question remains. Was building the world's highest railway ultimately worth it? When construction of the Qinghai, Tibet Railway was first announced, many engineers questioned whether the project was technically achievable. Others questioned whether it was economically justified. After all, the railway crossed one of the most remote regions on Earth. Thousands of bridges, long sections of elevated track, permafrost stabilization systems, high-altitude construction camps. specialized rolling stock, and years of research made it one of China's most challenging railway projects. From a purely engineering perspective, it demanded solutions that had never before been applied at such a scale. But infrastructure is rarely judged only by construction costs. Its true value is measured over decades. Today, the railway carries millions of passengers every year while also transporting essential freight across the plateau. Food, construction materials, medical supplies, fuel, and industrial equipment now travel by rail instead of relying entirely on long-distance highways. Rail transport also improves efficiency by moving large volumes of cargo with significantly lower energy consumption per ton than road transport. Beyond transportation, the railway became a living laboratory. Technologies developed for stabilizing permafrost, monitoring frozen ground, and operating railways in extreme environments are now influencing engineering research far beyond Tibet. Sometimes, the greatest achievement of a megaproject isn't the structure itself. It's the knowledge created while building it. And that knowledge may shape the next generation of infrastructure in some of the world's harshest environments. But even after solving countless engineering problems, one question still remains. Could an even more ambitious railway be built in the future? The Qinghai, Tibet Railway proved something many experts once believed impossible. Modern engineering can overcome environments that were once considered unreachable. But future railways won't simply copy its design. They'll build upon it. Researchers continue studying smarter methods of protecting permafrost. New materials with improved thermal performance could reduce heat transfer into frozen ground. Fiber optic sensing systems are making it possible to monitor track movement continuously over hundreds of kilometers. Artificial intelligence is beginning to analyze weather patterns, ground temperatures, and infrastructure performance, helping engineers identify potential maintenance issues before they become operational problems. Future high-altitude railways may also rely on increasingly automated inspection systems. Drones, autonomous monitoring vehicles, and satellite-based deformation measurements could allow engineers to observe remote infrastructure with unprecedented precision. As climate conditions continue changing, these technologies will become even more important. Because the greatest challenge is no longer building infrastructure in extreme environments. It's ensuring that infrastructure remains safe and reliable for decades after construction ends. The Qinghai, Tibet Railway demonstrated that engineering doesn't stop when the final track is laid. In many ways, that's when the real work begins. There are railways built for speed. There are railways built for profit. And then, there are railways built simply because people refuse to accept the word impossible. The Qinghai, Tibet Railway crosses one of the highest, coldest, and most demanding landscapes on Earth. Not by overpowering nature, but by understanding it. Engineers learned how frozen ground behaves, how thin air affects both humans and machines, how bridges could preserve permafrost, how passive cooling systems could protect an entire railway without consuming electricity. Every kilometer represents decades of research, countless field tests, and thousands of engineering decisions hidden beneath the tracks. Most passengers will never notice the thermosiphons beneath the embankments. They'll never see the sensors monitoring the frozen ground, or the calculations that keep the railway stable through changing seasons. They'll simply look out the window and see one of the most breathtaking landscapes on Earth. That's the mark of truly great engineering, when the impossible feels ordinary. The Qinghai, Tibet Railway isn't remembered simply because it's the world's highest railway. It's remembered because it redefined what engineers believed was possible. This is Echoes of Power. If you enjoyed exploring one of the greatest railway megaprojects ever built, subscribe for more documentaries uncovering the engineering, innovation, and infrastructure shaping our world. Because behind every impossible journey, there is an even more extraordinary engineering story.